Next, we will be talking about simplifying expressions, and in particular, simplifying expressions by factoring, which will lead us into solving equations. Before we start factoring, let's talk about how to find the largest common factor, so the thing that we're actually going to take outside of the brackets. Let's take a look at this example here. A squared b squared c and b cubed c to the fifth. I'm going to go through each variable one at a time to see what it is that these two things have in common. So in terms of a, there are two factors of a here, a squared, but there's no a's here, which means that the two terms have no a in common. In terms of b's, there's b squared here and b cubed here, so that means that in common they have two factors of b, or b squared. For c, the first term has one c, and the second term has 5 factors of c, which means that in common they have c. So notice, for example, that one of the other common factors you can say they have is just b, or just b squared. But that's not going to be the largest common factor. The largest common factor is the biggest part that both of these terms have in common, and determining the largest common factor will really allow you to do the most efficient factoring. Moving on to the next example here, the logic is going to be the same, except for we're going to do it with two terms that both have numerator and denominator. Let's look at numerators first. I noticed that between 3 and 15, there is a common factor of 3. Next, going through x's, I noticed that there's 2 factors of x here and 1 factor of x here. So in common, they have 1x. And then z versus z cubed, I'm going to have a 1 factor of z. On the bottom, the constants are 1 and 4, so nothing in common. And there's 1 factor of y that these guys share. For this last example here, it's all exactly the same, except now I have 3 terms, so I'm going to have to be a little more careful with checking. For numbers, I have 15, 3, and 5. So all 3 of them don't have anything in common. For a's, there are 3 factors here, 1 factor here, and no factors of a here, which means that I cannot take a out. They don't have it in common because the last term has no a's. For b's, I have b here, b there, and b squared, which means that I can take out 1 factor of b. And going through c's, I notice that it's c, c, and c squared, which means that I can also take out 1 factor of c. Excellent. So once we're able to determine largest common factors, we are able to proceed into actually factoring expressions that involve those factors. So I notice here that the largest common factor was b squared c, and the next step is to proceed to, in fact, take it out. So looking at the term one at a time, let's take a look at this one. If I take away b squared c, what is going to be left? Well, this one is pretty obvious. There's going to be a squared left. The operation in between was a plus, which means that I will preserve that operation. And then I'm going to take a look at the second term, b cubed c to the fifth. If I take out b squared c, what I'm going to have left is 1 factor of b and 4 factors of c. Notice that once you finish this, you can always check by opening up the brackets and making sure that you get the original expression back. This is also where you can use your exponentiation rules to make sure that you have the right powers. So if I multiply, for example, these two terms together, I notice that b squared times b will produce b cubed, and c times c to the fourth will produce c to the fifth. Okay, moving on to the next example, 9x to the fourth minus 3x squared. In terms of constants, I notice that I can take out 3. In terms of x's, I notice that the two terms have x squared in common. So once I take that out, I take a look at 9x to the fourth. If I take out 3x squared, what's going to be left is 3x squared. The operation was minus. And then the second term is 3x squared. If I take out 3x squared from 3x squared, what is going to be remaining? You got to be careful here. It's not going to be nothing. There is a factor of 1 there, and that is what's going to stay behind. Notice that if you didn't include this, then you could check by opening up the brackets and noticing that 3x squared times 3x squared will just give you 9x to the fourth, and you will have had a missing term. So this minus 1, when multiplied by 3x squares, is what produces the minus 3x squared here. So please notice that, please make sure that you don't actually lose this -1 when something gets factored out entirely. For this example here, it's a little bit different because notice that what we have in common now is this entire bracket of x minus 2. So let me highlight it to make it a little more obvious. This whole thing is what we have in common, which means that it's that whole thing we actually can take out. So if I factor out x minus 2, what I have left from the first term here will be 5, and the second x minus 2, plus, and then if I take out x minus 2 from this term, I will only have 6 left. You can simplify this a little bit further, of course, by opening up the brackets in the second brackets here and then combining like terms. So we're going to have 5x minus 10 plus 6, so minus 4. All right, let's take a look at an example with fractional powers. So notice that 2 to the 5th is bigger than 1 to the 5th, and what they have in common is x to the power 1/5. If I take that out using the laws of exponents that we've just covered, you'll notice that from the first term, I have x to the power 1/5 left, minus, from this guy, I took out x to the power 1/5, so we'll only have minus 3 left. And for this last example here, I noticed that this example is somewhat similar to the previous one where we factored out the entire bracket, except for our brackets don't quite match up. And I noticed that the first thing I can do is actually change slightly the second bracket. I can of course factor everything out and then deal with that, but it's actually a little bit easier to keep things intact if they already show some commonalities. Notice that I can factor out 2 from this bracket, and then it will look exactly like that bracket. So I factor out 2. What I have left is 2 minus 4x. And now I can take out this entire bracket that the two terms have in common. So 2 minus 4x, and what am I going to have left? From the first term, I have x squared left, and from the second term, I have 2x times 2, or 4x. Okay, and if you want to simplify it a little bit further still, you can notice that here, this bracket still has a common factor of x between the two terms, so this is also something that I can take out. 2 minus 4x, x plus 4. Okay? This is simply factoring common factors. But there's another type of factoring, and that is using various formulas. We've already seen one of these formulas before, and that is the difference of squares formula, except for here we will be using it kind of like in the backwards direction. So if you notice something that looks like the difference of squares, it means you can factor it out as the product of the two conjugates. The other useful formulas include square formula for the sum and the square formula for the difference. So once again, remember that these are not just x squared plus y squared or x squared minus y squared. Rather, you actually have to FOIL it in, and you will get that middle term. So x squared minus 2xy plus y squared, which means that if you see something that is reminiscent of this form, you are able to FOIL it back in. The other types of things are, of course, quadratic formulas and general quadratic equations or expressions. A lot of times you are going to be able to factor it out just by using the known method of trying to match up the two numbers that multiply together to be something and add together to be something, and we'll see how that works momentarily. So taking a look at the first example here, 81s squared minus t to the fourth, we immediately notice that both of these terms are squares of something. So I can rewrite 81s squared as 9s all squared, and I can rewrite t to the fourth as t squared all squared. This way, the true nature of this expression becomes apparent as something squared minus something else squared, which immediately means we can use the difference of squares formula that tells us that we can factor it out into the difference of the squares of the two terms times the sum of the squares of the two terms. And as I said before, you can make sure that this is correct by foiling everything back out and seeing that the expression you get is equal to the left-hand side here. For the next one, x squared plus y squared. So notice that the difference of squares, there's a formula for that, but there's nothing in our useful formulas here that will give us just the x squared plus the y squared. Every time we see the sum of two squares, it comes with an additional middle term being added or subtracted from it. So unfortunately, the sum of squares cannot be simplified. For the quadratic type equations, one simplest method to use is to try to think of two numbers that multiply to be -6 and add to be -1, which will give us the corresponding constant and linear coefficient. So the two numbers that will work in this case are going to be +2 and -3, right? So once again, double checking, these two numbers have to add up to be -1 and multiply to be -6, which works out. The other way to do it is using quadratic formula, which we're going to talk about later. Now, for the next equation, notice that there is a very, very close similarity in form to the equation above, where you can say that you have something squared minus something minus 6. It's just your something happens to be x squared now, not just x, like it was in this case. But the thing is, factoring works no matter what goes inside, so I can factor this out exactly the way I've done before, except for my something now gets replaced by x squared. So in this case, I'm going to have x squared plus 2, and then x squared minus 3. Okay, so once again, you can double check by opening the brackets, foiling them out. X squared times x squared is x to the fourth, minus 3x squared plus 2x squared will give you the necessary middle term, and then the two terms multiplied together will give you -6. The sum of squares is not going to simplify to be anything, but the second formula, if you wanted, you can break down further by using the difference of squares formula. Now here, notice that the first term once again remains as is, but the second term, the first is a clear square, but this 3 we can think of as root of 3 squared. So when factored out, this will be x plus root 3, x minus root 3, according to the difference of squares formula. Factoring comes in really handy when we're trying to simplify fractions and cancel out common terms from the numerator and denominator if possible. So let's take a look at how this works. In the numerator here, I have a quadratic, and we're going to apply a similar method as we did here, except for notice that our coefficients are slightly different. So in this case, I'm actually going to have -2 and +3. They still multiply to be -6, but now they add up to be +1, not -1. And on the bottom, I have a factor of x minus 2. Now, once I factored it out, remember that only common factors can get cancelled. So once I have factors, I can indeed cancel out the two terms, and altogether, I will have x plus 3 remaining. In the next example here, let's take a look at what we have. So the two terms on the top have x squared in common, so I can factor that out, and I will have x plus 9 remaining. And on the bottom here, notice that I can, of course, take out the 2, but the negatives are kind of awkward too, so I can also take out -2. You can always take out -1. In this case, I'm going to take out -2. If I take out minus 2 from the first term, I'm going to have x left. If I take minus 2 from negative 18, I'm going to have plus 9 back. And I see that this, in fact, produced two of the common factors on top and bottom, so I can very well cancel them out and have x squared over 2 left. All right, moving right along, let's take a look at this polynomial or trinomial in this case. Notice that all three terms have an x in common, so I can take out an x first of all. And once I am down to a quadratic, things are looking up. It's very difficult to factor out anything that is higher than degree 2. For quadratic polynomials, we can use the methods we have seen before, as well as quadratic formula, but for cubic and anything above, we don't actually have very good formulas. So we're just hoping that we'll get lucky and the polynomial ends up somehow working out. Now here we were able to take out the x from all three terms, leaving us with a quadratic. So taking a look at this, I need to think of two numbers that multiply to be 9 and add to be negative 6. And these two numbers actually work out to be 3 and 3. So this is actually x minus 3 squared divided by x minus 3. Now notice too that I've actually used this formula, but without really applying it directly. I could just always think of the two numbers that need to multiply to be the right things, but it's actually exactly this formula that is at play here. So take a minute and try to see how this worked out. Now, once I have the two common factors, I can cancel them out. And so altogether, I'm going to have x times x minus 3 in this case. For this last one in this column, let's take a look at the top and bottom. The top is a clear difference of squares, so I can have 5 minus x and 5 plus x. And on the bottom, I have x minus 5. So I notice that x minus 5 and 5 minus x are exactly the same except opposite in sign, which of course means that I can take out minus from the bottom and flip the signs of everything. Okay, and now I notice that 5 minus x and 5 minus x here are the exact same factor, so they can get canceled out. The minus that I factored out will remain, but it doesn't have to live on the bottom. There's nothing else on the bottom, it's just minus 1. So let me first rewrite that as with negative 1 on the bottom, but it's the same as multiplying the whole thing by minus 1. So really, this is just minus 5 minus x. Okay, let's take a look at this one here. Once again, the top here looks like it can be factored out as a difference of squares, and in fact, we've done that here before. So this will be x plus root 3, x minus root 3. So not every square in a difference of squares has to be a perfect square. It could result in a square root. And then with the corresponding factor on the bottom, I can cancel those two out to have x minus square root of 3 left. For this next one here, there's nothing to simplify on top, and the bottom is a sum of squares, which cannot be simplified, so this entire thing can't actually be simplified any further. And that's okay. Some problems don't have very nice solutions or no solutions at all. For this here, one word of caution right away too is because there seems to be so many 3's, please don't just start haphazardly canceling things out. This is not right because these 3's are not common factors of top and bottom, so don't do that. But in order to acquire common factors, well, I can notice that I can factor out 3 from the top, but if I take out 3, I'm going to have x plus 1 left, whereas the bottom has x plus 3. So the top and bottom still have no common factors, so I can't actually simplify this any further. For this last one here, the bottom, again, there's nothing to simplify there, but the top looks like I can actually take apart as the difference of squares. So the difference of squares here will be x squared minus 3 and x squared plus 3, right? Be careful, it's going to be x squared because the original was x to the 4th all over x plus 3. So notice too, again, that there's nothing I can do with the sum here, but I could break apart this difference of squares once again, just like we've done before. But if I do that, or rather when I do that, I'm still not actually going to acquire any common factors with the bottom. So this, in fact, is more or less as simple as it's going to get. So I'm going to break up the top into one more factor, but I'm not going to be able to cancel it with anything on the bottom, really. Okay, so this is as factored out as this expression is going to get. Please take a look at WebWork Assignment Module 1C for more practice with factoring in various ways, because this will be essential in the next part of Module 1, which is all about solving equations.